This video is a continuation in our series of videos where we are using calculus to analyze functions and hence be in a position to make sketches of them. In the previous examples A, B, C, D, E, and F, we have been looking at functions that are polynomials. In this video, we're going to look at functions that involve the exponential function. Okay, so we're going to start with example number G, where we have got x squared e to the minus x. So before we apply calculus here, it's going to be useful just to get a feel of what this function might behave like. So we have got this function is formed, it's a product of two functions. First, we have got e to the minus 2x, which we know looks like that. The y-intercept is 0, 1. And then we have got x squared, and then we're multiplying these two. So x squared, again, we know looks something like that. So the first thing we notice is that both of these functions are positive everywhere. Let me just say both of these functions are non-negative. So this one, x squared, when x is 0, it's going to be 0. So we expect that this function is typically going to be greater or equal to 0. So its graph should entirely be above the x-axis, just like it is the case with these two graphs here. Okay, so with that in mind, let's see what calculus is going to enable us to unearth. So if we do the first order derivative, so this is going to be 2x minus x squared times e to the minus x. And then the second order derivative, again using the product rule, is going to be 2 minus 4x plus x squared all times e to the minus x. And so now we are in a position to find our stationary points. As we have established, these are found by taking the first order derivative, equating to 0, and then solving. Now for this equation, since e to the minus x is never equal to 0, then what this equation tells us is that the only way this thing can be 0 is if 2x minus x squared is 0. Just notice here that that should be e to the negative x, not negative 2x. So it's negative x here. Let's redo that line. So this quadratic equation gives us two solutions: either x is 0 or x is equal to 2. So we have got two stationary points. The first one is going to serve as well as the y-intercept. So plugging into our y equation, when x is 0, y is going to be 0 as well. And then in terms of concavity, if we plug this into the second order derivative, so there's the second order derivative. If we plug in x is 0 there, that is going to give us 2, which is positive. So this is telling us that the function at 0 is concave up. So we have a local minimum at 0, 0. So this is a local minimum. Then next we look at the stationary point when x is equal to 2. So again, the first thing we're going to do is to plug in x equal to 2 into the y equation, so that we've got the y coordinate. We're going to have 4e to the minus 2. This is the same as 4 over e squared, or if you like, just 2 over e all squared. Okay, so that is going to be the y coordinate when x equals to 2. As far as the second order derivative is concerned, so if we plug in x equals to 2 here, we're going to have 2 minus 8 plus 4. So 2 minus 8 plus 4, and then e to the minus 2. So that's 10 minus 8, so this is going to be 2 over e squared. So the main thing here is that this is positive because e squared is positive. So if this is positive, actually there is a problem here. This is 2 plus 4, which is 6, minus 8, so this is negative 2. So that thing is actually negative, so it's concave down at x equals to 2. So we have so 2 4 over e squared, which is the y coordinate. So this is a local maximum. Okay, so we have got we have characterized or found the nature of our two stationary points. All right, so maybe, okay, let's make some headway with the sketch. So the graph of this thing should just be in the first and second quadrant, because we have seen that it's either going to be 0 or positive. So at the origin, the graph looks something like this, and then at x equals to 2, the graph looks something like that. And that is all we know so far. So this indeed is suggesting that the graph might go something like this. But this side, we are not sure. All we know is that it's going to be above here. For this case, it's going to help us to go on with the second order derivative and analyze the issues of concavity. Then that's going to help us with the shape of the graph this side. It looks like between here and this side, it looks like we already have a picture of what the graph is going to look like. So let's go to part 3 and look at the inflection points. So the inflection points are going to be where the second order derivative is equal to 0. Again, since this cannot be equal to 0, what this is implying is that the quadratic is the 1, or where the quadratic is equal to 0, that is where we're going to have our inflection points. If we solve this using any method, we find 2 points. One is 2 plus root 2, and the other one is 2 minus root 2. Now both of these are positive because root 2 is less than 2. So 2 plus root 2 is greater than 2. 2 minus root 2 is less than 2, but still positive. So these are located symmetrically with respect to the second stationary point here. So what is happening is the concavity changes at these 2 points. We already know that this side concavity is up and this side concavity is down. So the point in the middle here, let me just go back to our sketch now. The point in the middle here where the concavity changes from down to up must be 2 minus root 2. So remember, this one is x is equals to 2. And then what it is saying is that equidistant to this one, this side, the concavity changes from down to up again. So if we go on with our graph, it means this graph is going to be concave down and then change to concave up, and the point where it is going to change is 2 plus root 2, given by these two. So what this thing is telling us is that as the graph goes to infinity, it's going to go closer and closer to the x-axis, but it's going to be curving upwards as opposed to curving downwards. And then of course this side there is no inflection point, so we can now do a full sketch of this. So the graph is just going to look something like that. So that completes the sketch. All right, so now let's just write down the concavity intervals. So we can see that this is going to be concave up over, so everywhere between 2 minus root 2 to negative infinity, this thing is concave up, and then the right hand side of 2 plus root 2, it's concave up as well. So that is from minus infinity to 2 minus root 2 union from 2 plus root 2 all the way to infinity. And then it's going to be concave down only between those two numbers there. So between 2 minus root 2 and 2 plus root 2, then it is concave down. And then the areas of increase and decrease, those ones are separated by the stationary points. We've got one here, got another one there. So on the left hand side of the origin, the graph is decreasing. On the right hand side of 2, the graph is decreasing as well. So we're going to have decreasing over, so we can just say for x less than 0, and then for x greater than 2, and then it's increasing only between 0 and 2. Right, so that gives us a kind of full picture of this graph. Now, as you can see here, we have used the full use, we've made the full use of the first and second order derivatives. For the polynomials, typically, the use of this was minimal in giving us a picture of what the sketch is going to look like, but for these functions we need to use all the derivatives. Okay, at this point we are going to give you a chance to have a go at these two others. If you want to pause the video and have a go at H and I, and then when you continue the video you can compare with our solution. All right, so we now look at the last two examples, H and I. So in H, again, we're going to start by plotting the two functions that make up our given function. First, got 2x, and e to the minus 2x. This time we're adding them. So you can see that this side, as x becomes bigger and bigger, this becomes smaller and smaller. So we expect that the sum of these will be dominated by the straight line. But on the left hand side, this one we expect to dominate because it gets headway. It's already 1 here while this one is 0. So but we will see. So that just helps to give us an idea of what might happen. So here are the derivatives. So if we set the first order derivative to 0, we find that the stationary point is at x equals to ln half. Then if we plug this into our y, we can actually work it out to a compact ln e squared over e over 2 squared from this. And when it comes to the concavity, the second order derivative is this. This is always positive. Okay, so that means this can only be a local minimum, because this positive means that the graph is always concave up. So we have got one local minimum. In fact, it's going to be a global minimum as well, or an absolute minimum. So there are not going to be any inflection points because this does not vanish at any point. The y-intercept is 0, 1, so then simply our function is going to look like this. Always concave up, decreases up to the stationary point, increases after the stationary point. And this side we expect it to be very much similar to 2x. Okay, so that's that. Then for the second one, again, if we start with the two functions, in this case two functions making this up is 2x plus 1 and a to the minus x. We're multiplying them this time. So again, as this goes to big values, this goes to 0, that goes to infinite. When you multiply, we expect that to go to 0. And then this is negative 1/2. So on the left hand side of 1/2, when you multiply these two, we expect to get a negative. So we expect this to go down and then to go to 0 this side. So first order derivative is this, second order derivative is that. If we take this and equate it to 0, we find that the stationary point is at x equals to 0. If I plug into the y, that gives us the y-intercept as 1. And of course, we expected that because both of them go through 0, 1. For the second order derivative, if we plug in x is 0 here, you find minus 4. So that gives us a local maximum. And if we go to look for the inflection point, we find an inflection point at x equals to half. So that means on the right hand side of the origin. So in terms of the graph, maybe let me just do this from scratch. So in terms of the graph, what's going to happen is we know that we have got a maximum here. We know it goes through negative half 0, so it's going to go through there. And then at half, it changes concavity. So it's concave down up to there, and then from there it changes to be concave up, and then it approaches the x-axis asymptotically. So that's what the graph is going to look like. So of course, in terms of concavity, concave on the left hand side of x equals half, concave down, concave up on the right hand side of half, increasing up to x equals 0, decreasing after x equal to 0 on the right hand side. All right, so thank you very much. Hopefully it has been useful. Please do not forget to subscribe, of course, to our channel so that we can produce more stuff like this one. Thank you.